Chapter 3, Mass Relationships and Chemical Reactions. This is a very, very important chapter. We start out with getting atomic masses, atomic weights, going through balancing equations, finally getting into conversions, and into stoichiometry. Basically using different values, almost like a recipe from a reaction, figuring out how many products will be the result. First off, atomic mass. The mass of the atom in atomic mass units, AMUs. 1 AMU is exactly equal to 1/12 the mass of one carbon-12 atom. So this is a unbelievably small value. One carbon-12 atom, and we're talking 1/12. We're basically saying here that each proton and each neutron, which are about the same mass, each one of those weighs 1 atomic mass unit. Down the bottom there, since elements have isotopes, the average atomic mass is used. We know that there's not just carbon-12, there's also 13 and 14. So we need to take what's called a weighted average. We don't have equal amounts of 12, 13, and 14. In carbon, in our part of the universe, it's almost all carbon-12. There's a very small amount of 13 and 14. What we can do is calculate the average atomic mass. Here we see an example with the two stable isotopes of boron, boron 10 and boron 11. We see that it is predominantly boron 11 at over 80%. So out of all the boron in the world, 80% of it is boron 11, about 20% of it is boron 10. We'll see this calculation two ways. One, they give you precise atomic mass units for the two isotopes. To calculate the average atomic mass, we use a basic weighted average. Instead of just taking the two and adding them up and dividing by 2, or just our regular average, what we're going to do is we're going to use the percentage that each one is in abundance. All we do is we take our percent abundance, we take it from a percent and turn it back into a decimal, and then we just multiply it by the mass. Put them together, just add them, and that's how we get our average atomic mass in atomic mass units. So for boron, it's 10.81. We might also see this another way. They might not give us those precise values, so instead what we'll do is we'll say that boron 10, since it has 10 protons and neutrons combined, we're just going to say that that weighs 10 AMUs. And same thing with 11. So there we do our calculation. We get 10.8 AMUs, just about the same as we did the other way. Again, what they could do is give you the average atomic mass and the isotopes, and what you would do, and they might say, what is the percentage or percent abundance of each? You can call this X. So then this one would be 1 minus X, and you can just solve it algebraically. The mole, big topic in chemistry. A mole is just a way that we count. All right, it's the same idea as a dozen. A dozen is always 12. If you have a dozen hats, you have 12 hats. A dozen eggs, 12 eggs. If you have a mole of hats, you would have 6.022 times 10 to the 23rd. If you had a mole of eggs, you would have 6.0222 times 10 to the 23rd eggs. So all this is, we call this Avogadro's number, and it's the way that we count. Since atoms are so small, it doesn't make sense for us to count individual atoms or to do calculations with individual atoms. Instead, we're going to use the concept of the mole, the idea that we're going to take these really small things and we're going to, instead of counting each individual one, we're going to look at a large sample of them, and that's what our mole is. Our molar mass is exactly what it sounds like. The mass of 1 mole of our substance. And this is measured in grams per mole. On the periodic table, we have our masses that are there. These can either be in AMUs if you're talking AMUs, or they could be talking in grams per mole. We're going to use them in grams per mole. We virtually never use AMUs. All right, all these things mean the same thing. Atomic mass, atomic weight, Molecular mass, molecular weight, molar mass, formula weight, all of these things are the same thing. We get it from the periodic table, we find out their values, add them up, and we'll get our molar mass, how much 1 mole of a substance would weigh. All right, so here are some examples of moles. We have what looks like a mole of water. This one looks like water to me. We might have a mole of mercury right there. We have a mole of possibly salt or sugar, a mole of graphite, which is carbon, and this looks like a mole of iron. So again, these are different values, there's different amounts. They're all the same number of particles, but they would weigh different amounts. They'd have different masses. All right, this is how I'd like to see you guys calculate the molar mass, or the molecular mass, whatever you want to call it. I would give you a substance, here calcium carbonate, CaCO3. First thing we do, we write down our elements. We have 3 elements. We have Ca, C, and O. What I want you to do is write down how many of each you have. 1 Ca, 1 C, 3 O's. From the periodic table, we get its molar mass. On our periodic table, calcium might be 40.08. We're always going to round off, so we have one number to the right of the decimal. Since it's 40.08, we're going to round up to 40.1. Carbon 12.0, oxygen 15.9994. We're going to round that off to 16.0. All we do next is multiply the number of atoms times their molar mass. We get this subtotal here. We get the 3 subtotals, we add them up. So this is saying that if we had 1 mole of calcium carbonate, it would weigh 100.1 grams. Next up, magnesium nitrate. Here what we need to remember is to distribute, just like in math, this 2 to the nitrogen and the oxygen, because that 2 is saying we have 2 groups of NO3. So magnesium there's 1 of, nitrogen there's 2 of, oxygen there's 6 of. So we distribute that 2 to both the nitrogen and the oxygen. Look on the periodic table, get the molar masses, get our subtotals, add them up. 148.3.